of these 1,3 diaxial interactions, right? It's a 1,3 diaxial here. The reason why we call it 1,3 is that carbon 1, 2, and 3, and these are both axial. So this is the 1,3 diaxial here and the 1,3 diaxial over here. So there's two of those kinds of interactions, right? So it adds up to 7.6, right? Then for an ethyl, that energy cost is 8 kilojoules per mole, so just a little bit more. But you can see what happens when we go from an ethyl to an isopropyl. So if I have an ethyl, you can imagine that I can have my other carbon CH3 here, right? Can kind of avoid that 1,3 diaxial. If I have isopropyl, now it's starting to get more congested, but I can still get away from a lot of it because I can put my two carbons here. So they're not pointed directly at these other axial substituents on the cyclohexane ring. But once I get to T-butyl, I have no choice. No matter how I rotate this, I'm always going to have a methyl group that's pointed right at or pointed pretty much in the same direction as these 1,3 other groups. So for T-butyl, the energy price is huge, right? 22.8 kilojoules per mole energy, higher in energy to have that T-butyl in the axial position. So how often do you think you're going to have a T-butyl in the axial position? Not very often. You have to have something else that's going to be more favorable to be in the equatorial position to be able to overcome that. All right, see you now. Thanks for letting me know.
Oh, you're welcome.
Does everybody understand this? So the equatorial position is going to be more favored, always going to be more favored if you have a single substituent, and the axial is going to be the one that's higher in energy if you have a single substituent, right? There's some tricks that you can do so always, and it's sort of like the usual always that you get from a chemistry professor, right? There are some systems that we could hop up to make it change that, but if it's just a regular old cyclohexane with an alkyl group attached, then it's always going to be that the equatorial is more stable, and therefore you'll have a higher amount of that configuration at equilibrium. Right? And so this just reflects the ratio of equatorial versus axial here. First number is the equatorial, the second is axial. About 6 kilojoules per mole is equivalent to a difference by about a factor of 10. So you can see here that for the methyl, 7.6 kilojoules per mole is going to be a little bit more than 10 to 1 ratio. So if we take the 95 divided by the 5, right, it's about a 19 to 1. Right, so it's almost, it's a 2 times and then 10 times. So 20 times. But when you get down here to isopropyl, it's 9, so it's almost, you're getting up to a little closer to the 2 factors of 10 here, 97.3. And then for a T-butyl, you can see that this is, if you divide that by 6, it's more than 3 of our orders of magnitude, 10 by 10 by 10. So it's a lot, right? Almost 4 orders of magnitude more of the equatorial versus the axial. 10 times 10 times 10 times 10, right? All right, everybody understanding it? This is important stuff, so I'm going through it a little bit slower than some of the things that I've gone through in recent lectures. All right, so now it gets a little bit more complicated. So if you have one substituent, it's pretty straightforward, right? If I have a T-butyl group, man, that thing's going to be locked in the equatorial position. You'd have almost none of the other conformation which has it axial, right? But what happens if I have a more complicated system and I have 2 substituents? Then what, right? So if I have 2 substituents, imagine if I have a chlorine and a methyl. And these guys are next to each other. Right? So imagine that I have my cyclohexane. I'm going to try to make this exact drawing, and it won't quite hold up here on my thing here. So I'm going to say, all right, so it's there like this. And I'm going to put my chlorine. Oh, it's grabbing the table. I'm going to put my chlorine right here. Oh, did I do it right? I have one down and one up. Right? And so did I do it right? Is that the right structure? So around my ring, I have a methyl, and it's down into the plane of the board if I were to draw this all up flat, right? And my chlorine is up and out, right? So I think I did it right. Did everybody see that? Everybody agree that this is correct? Yeah? So I have this. Now, in this system, we're talking about which ring am I going to have, because maybe I can access both of the different chair configurations, right? So if I have this, and I rotate this one up to put my chair, and I rotate this one down, that overall is the ring flip. I went from having both groups axial to having both groups equatorial, right? Can you see that? So if the groups are alternating around the ring system, one up, one down, one up, one down, I can have this configuration where both groups are equatorial. That's pretty easy, right? If I have both of my groups equatorial, I have the 7.6 kilojoules per mole favorability for having my methyl group equatorial, and I have my 2 kilojoules per mole favorability for the chlorine. And so overall, you're going to just add those two up. So overall, this is going to be around 9.6 favor versus the other one where they're both axial. About that. Okay? So that one's pretty easy. I can put both groups equatorial. Now what happens if I were to change this? If I can get it out. So that I do a different structure here, where they're saying both up. Now this becomes more challenging. Now, I have to have, now one's going to be axial, right? That methyl, it's axial, right? Can you see that? And the chlorine is equatorial. So now, like a lot of things in chemistry, I have to decide which is more important. Because these are opposing each other now. One, they both want to be equatorial, right? That's going to be the more favorable position energetically. And I have either this one, or if I do my ring flip, or there we go. Or I have this one, which has the chlorine axial and the methyl group equatorial. So which one's going to win? Does this one win or does the other one win? Because they're opposing each other, right? Which one do you think is going to be more problematic having in that 1,3 diaxial? The methyl group or the chloro? Which one's more problematic? The methyl. And why do you say methyl? Exactly, it's got the 3 hydrogens coming on. That makes it bigger. And when I have that 1,3 diaxial interaction, I just almost poked myself in the eye with the cyclohexane. I'm in the cyclohexane chair now. Getting right in the chair. Chemistry brought to life right here. Yeah. If I have it like this, right? The methyl group's bigger, it's going to be bumping into this hydrogen more than that chlorine bond. And that's why the 1,3 diaxial interactions of the methyl make it 7.6 kilojoules per mole higher in energy, and the chlorine is only 2 kilojoules per mole higher in energy. So between these two, the one where the methyl is equatorial this one is favored by the difference of those two energy amounts. So this one should be about 5.6 kilojoules per mole lower in energy than the other one, right? Which is almost about a factor of 10, right? 6 kilojoules per mole is a factor of 10. So this is going to be like, 10 to 1. If we're trying to put this into out of 100 or 100%, right, it would be like 91% this and 9% the other. So the ratio would be about 10 to 1, right? Does that make sense to everybody? Yeah? So if I give you a quiz and I say, you have these two substituents, you have to look at it. If you haven't memorized that whole table, which I think that that small set is worth memorizing. Methyl, ethyl, propyl, that's worth, isopropyl, that's worth memorizing. Right? T-butyl, holy cow. 22-point massive, right? It's huge. So that one is always going to want to be equatorial, and if you have your choice, you're going to always want to put the T-butyl equatorial, even if there's more than one substituent. Because if you have two methyl groups, that's going to add up to be around 15.2. But the T-butyl beats even two methyl groups. The T-butyl will force two methyl groups, if they're in opposition, to be axial, so that the T-butyl can be equatorial. So that it can beat out multiple different groups. Right? All right. Does that make sense? Yeah? All right. So we talked a little bit about two groups on there. And then let's talk about cis and trans. We're really going to cover that, I think, in the next chapter. But if we have two groups on a cyclohexane, right? Right now, these two groups are both up, right? One's axial, one's equatorial. We're still going to refer to these as cis, because if I draw this out flat, right? And I draw it flat, see if I can even get this to be flat. I probably can't, because these are really trying to be tetrahedral. But if I force this part of the molecule to be flat, so you can see that both of these are up, right? If I were to draw this out perfectly flat, which it really doesn't want to do, because these are all at, the carbons of this are all angled at 109.5. But if I could force this all flat, you could see that these are both up. So although when I draw my chair, right, they're kind of pointing in very different directions. One's axial, one's equatorial. They're both still up. So we would call this, they're both on the same side. And so we refer to this as cis. So when they're both up, so if we drew this out completely flat, if they're both up, that's called cis. And if I actually made this into a chair, one would be axial and the other one would be equatorial. So if two groups are on adjacent carbons and they're both in the same direction, one's going to have to be equatorial and one's going to have to be axial. Right? Now, if I do another little trick here, one more fun little piece of excitement. So, if I, okay, bear with me for just a moment. As I have this awesome model, and I'm going to put a whole bunch of orange balls on here, because I think this will be really cool. And now that you guys have seen this a little bit, we're going to do something cool here. And I'm going to say, for my next magic show, I need a volunteer. Who wants to volunteer? Anybody? 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 All right, come on up. All right, so we have a chair, right? Go ahead and grab the chair. However you want to hold it. You can be in the middle of it if you want. And the orange balls, what position are they in? Equatorial, equatorial, equatorial or axial? Axial. They're all axial, right? Now do a ring flip. So rotate this one, rotate it like this.
Okay. So,
Yep.
that way?
And then the other one the opposite way. I'll hold on to this one so that it's a little bit easier for me.
Okay.
Because that one has to now go up. Yeah, so rotate it so that it goes up.
No, I don't want to like.
Yep, like that. It's poking it up. There you go.
Yeah. Hold on. Like that.
Yeah, but I think you messed up this side when you did that.
Yeah, I think I did.
All right.
Okay.
There you go, right? So that's the whole ring flip. We flip one side, we flip the other side. Now when we're looking at these, right, all the orange balls were in all of the axial positions, right? Now where are they? So when you do a full ring flip, every substituent that was axial becomes equatorial. And everything, the white balls, thank you. The white balls, which were equatorial, are now where?
Axial.
axial, right? So if you're given a problem and you have to decide which is the most stable conformation, question would probably go like this. Here's your cyclohexane ring, you have your substituents on it, and they alternate, right? You have one up, one down, one up, one down. And you draw one out and you see that you have them all axial. If you do a ring flip, they're all going to be the opposite. So you have the choice of either having the alternating ones either axial or equatorial, right? But when you do the ring flip, whatever was axial is going to go to equatorial. Whatever was equatorial goes to axial. Make sense? Brought to you right here in 3 dimensions with this awesome model. Okay, so that's an important thing to understand also, because if you draw one out and you're like, wait a minute, if I do this like this is going to be axial. If I do this like this, it's going to be axial. You don't actually have to draw it again if you know when you draw it one way, it's all axial. Then you know if you draw it the other way, it would be all equatorial. Right? So if I want to actually, does everybody get this? I don't want to belabor this point. I could do a couple more things, but if you all get it now, then I think we can move on and just mention that we also have this trans configuration. So cis is when our substituents are on the same side. So if I'm looking at this substituent and this one, right now they're both up. If I'm looking at this orange ball and this orange ball, they would be one is up and one is down. So when one is up and one is down, they're on opposite sides, right? We call that trans. Right? So these are not constitutional isomers, though. Cis and trans isomerism is not constitutional isomers. Why is that? Why are these not constitutional isomers? Remember our pathway, right? We had the first part is, do they have the same chemical formula? If the answer is no, then they're not even isomers. If the answer is yes, we then look at the connectivity of the atoms. If the atoms have the same connectivity, right? If they have different connectivity, what are they? Constitutional isomers. If they have the same connectivity, what are they?
Identical.
They're stereoisomers, right? So this is sort of our first example of where we're calling it by a name, a pair of stereoisomers. So while the connectivity is the same, where they are oriented in three-dimensional space is different. Right? So these guys are stereoisomers.
Say that again, stereoisomers.
Stereoisomers. And in that graphic that we had last time, it's in that. But basically, there's a little bit more left in this chapter. A couple of slides. Here's one, right? Many important structures that result when more than one ring is fused together. So we talked about these bicyclos, camphor, campene, right? These are fragrant molecules. So we can come up with some more complex structures. This is just sort of like finishing off with polycyclic systems. And then, maybe every jeweler's favorite, if we have a system that looks like this, where we have a chair of all carbon atoms, right? It's got a 6-membered ring, all carbons, and it's connected to another chair, a series of chairs down here, right? So these connection points, this axial point is connected to an axial point here, and then on the sides, these guys are connected also to another chair. You have a carbon framework that's all chairs, right? And that very stable structure is diamond. Right? And if we look at sort of a 2-cyclohexane fusion here, right? So what would we call this really? It's sort of common name is Decalin. Maybe the guy who came up with this had a girlfriend. Her name was Declan. I don't know. Girl had a guy. I don't know. Declan, a boy or girl? I don't know. Boy name? So, anyway, that doesn't really capture what this really is. If we name this as a bicycle using the IUPAC naming system, what would it be called? We just name that parent. It is a bicycle, right? and we name the bicycle, we look at the number of carbon atoms that are in it. So it's got 1, 2, those are the bridgeheads, 3, 4, 5, 6, 7, 8, 9, 10. So it would be a decane, right? But it's a bicyclodecane. So it would be bicyclo, and then we have the brackets, right? And then what goes in the brackets? The number of carbons in each of those pathways between the two bridgeheads, right? So this would be, how many are here? 1, 2, 3, 4, right? So it would be bicyclo 4, and then on the other side we have 1, 2, 3, 4, right? So it would be 4.4 point, what's this? 0, right? So this would be called bicyclo 4.4.0 decade. But we have this common name for it, decalin. And we call this cis-decalin because this pathway off this chair here, this pathway here, it's down, right? That's down, it's equatorial here. And this one is axial, it's also down. So we have down, down, that's cis, right? Then transdecalin has these both in the equatorial position, but when you do that in adjacent carbons, one's going to be down and one's going to be up. So that's transdecalin. Make sense? All right. Yeah.
Can you say that one more time?
So if we look at this, you mean where the cis and the trans is coming from?
I'm getting
Yeah.
confused about that.
So if we just look at this chair here on the right, and we look at these groups here, and you can either look at the carbons coming off, or you can look at the hydrogens. Either one will answer this question. So this time I'll do it a different way. If we look at the hydrogens, right? That hydrogen and that hydrogen, are they both up, both down, or is one up and one down? They're both up, right? So they're both on the same side of that system. And since they're both on the same side, we call that cis, right? You can look at that either as the hydrogens or the carbons on here, right? And this one over here, you can look at either the hydrogens or the carbons. Technically, we should probably look at the hydrogens because it's the same atom type. Because if one pathway was different versus the other, then it's a more challenging system, right? But if we look at the hydrogen here and hydrogen there, are they both up, both down, or is one up and one down? One's up and one's down, right? And then if we look at the alkyl branches of this other ring, also one is up and one's down, right? This one's down, that one's up. This hydrogen is up, that one is down, right? So when they're on opposite sides, that's called trans. Okay. All right, so that is it for chapter 4. That's the last slide. There's some additional, oh, I have another one. I missed that one. Anyway, steroids, these are fusions of these ring systems. And I think that's the last slide. And then after that, we have a bunch of practice problems in here. So I would suggest that you guys do these practice problems in addition to your other out-of-class efforts to make sure that you're keeping up with being able to do the problems, not just understand the solutions to the problems, right? Any questions? If there aren't any questions, we're going to take a 5-minute break, and then we're going to get into chapter 5. Okay, so